So here we're looking at this function, this rational function that has a removable discontinuity at -2, all right? And you're asking me about function values, right? So this f of the function or g of the function, that's function notation. That's asking me for what is the value of this function at this x, okay?
Okay.
So the value of this function at -2 in this case doesn't exist, does it?
No.
It's not defined. However, the limit exists. Yeah?
Mm-hmm.
The limit, if I say the limit as x approaches -2 of f of x, if I want to say that, or if I want to say this function that I created, which is x plus 2 times x minus 2 over x plus 2, okay? This limit exists even though the function doesn't, because I can cancel these factors and say that that's equal to, this is equal to the limit as x approaches, I'm going to use the greater than for that. The limit as x approaches to, -2 rather, sorry. Limit as x approaches -2, I can cancel these factors and write x minus 2, x minus 2. This is equal to -4.
Mm-hmm.
Okay. Now, the function is undefined, but the limit exists. But since, this is what you were trying to say, since the value of the function does not equal the value of the limit, the function is not continuous at this point. Yeah.
Mm-hmm. Okay.
So the limit can exist. What you need to remember is a limit can exist when a function is not defined. It doesn't have to. Sometimes when a function is not defined, the limit doesn't exist either. Right?
Okay.
But sometimes, like here, the function is not defined, but the limit exists, right?
Mm-hmm.
Now,
Okay.
suppose that I gave you this example. Suppose that I said, let me change this. So let me go over here and change this. Suppose I said this. Suppose I said y equals, let me clear the drawings. Suppose I said this. Y is 1 over x minus 2. Okay? Now, that's a different graph, right?
Mm-hmm.
And suppose that I'm approaching, now suppose that I want to evaluate f of, find f of, let's do this. What is f of 0?
Oh, okay. Don't you have to put in then 0 for y?
No, this is telling me where the input goes. So it's going to be my
Okay.
X term.
Okay.
So I'm going to put it
Okay.
in and it's going to be Y. This is going to be this. So this is going to be Y equals 1 over 0 minus 2. Okay?
Mm-hmm.
0 minus 2. That's equal to negative 1/2. Okay? Y equals a negative 1/2. So this point is 0 and negative 1/2. There it is. There's my point
Okay.
right there, right?
Mm-hmm.
Now, f of 0 is a negative 1/2, right?
Mm-hmm.
What is the limit as x approaches 0?
As x approaches 0,
Mm-hmm.
from which side? Just both sides?
Yeah, exactly. If I
Okay.
don't specify, it means both, right?
Okay.
So if I'm approaching from the left
It's
and
gonna
I'm
be
on this branch and
it's gonna
my
be
y value
negative one
is
half.
negative 1/2. If I'm
Okay.
approaching from the right, then I'm down here. Because remember, I hop up there, right? Then
Mm-hmm.
I jump down and I hop up here and I go this way. And it's
Okay.
still negative 1/2, isn't it?
Right.
So this function is continuous at 0, isn't it?
Mm-hmm.
We don't have a problem at 0. Now, what about this? Let me draw something else in here. X equals 2. But let me draw it in as dotted for you there. Now, that line is an asymptote, isn't it?
Mm-hmm.
Right? So if I ask you to find me, if I asked you this question, what is the limit as x approaches 2? The limit as x approaches 2 of 1 over x minus 2, what would you say?
Over x minus 2. Isn't that undefined?
Look at the graph.
Right?
Well, it is. It's okay. So the function is undefined, right?
Right.
The function is undefined. What would we say about the limit? That it's what?
About the limit.
It does not exist.
Okay.
Does it?
Okay, I thought that, okay, I was gonna say, where are you going? Okay.
It doesn't exist, does it?
Yeah, yeah, that makes sense.
The terminology is a little bit different, but
Yeah.
it's essentially the same thing. The limit doesn't exist. Now, it doesn't exist for a different reason than in the other graph we did.
Okay.
Okay. This
It's
graph
because,
has a discontinuity at 2, doesn't it?
right, yeah.
But
It's
it's
called,
not,
isn't it an infinitive
it's
discontinuity? Or
wrong,
something
wrong
like that?
class. Infinitives are for language classes.
Sorry.
Infinite is for math classes. Um, yes, it's an infinite discontinuity or an asymptote.
Sorry.
That's fine. Yeah, this is an infinite discontinuity, right?
At least we're getting that out of the way before the, the AP test.
Now, in this case, so here, if I ask you what is f of 2, right? what
Mm-hmm.
would you say? If I just asked you for f of 2, right?
F of 2. Okay.
So plug 2 in here, what do you get?
Just 1 over 0.
Which is what?
Does not exist.
Right, that's
Oh,
undefined, right?
right.
So the function isn't defined here, is it?
No.
So, okay, so let me try and help you a little bit with this. Let's take a picture of this and let's see if I can help you put this together a little bit, because you're about 80% there, but I think
Okay.
you're overthinking it just a bit. All right.
No, I'm trying not to. I'm just like,
I
ugh.
think it's you're just a little bit. It's not serious, but I think it's kind of giving you a bit of a it's giving you a little bit of a headache right now.
That I will agree with.
If I said, let's go back to this. Let's go to this function here. F of x is equal to, let's do this one, okay? Because we just finished looking at it. Let's do this one. 1 over x minus 2, right?
Mhm.
Now, a couple of things I want to point out and have you remember, because I think you're getting this confused too. All right. If
Okay.
there's a difference between me asking you what is f of 2, okay? Now we're not doing any calculus right now. Give me a minute. We're not going to do any calculus for a minute. This is algebra. What is f of 2 versus um when is f of x equal to? Okay, those are different.
Okay. Yeah, I learned that one the hard way.
First, I want you to see,
Okay.
and I know this is overkill, but I want you to see this. Here, the 2 is on the inside of your function here, right?
Okay.
Here, it's after the equal sign, okay?
Mm-hmm.
Now, if this was your sport, this is where your coach takes you aside and you diagram the play. We're having a coach's timeout right here, okay? Function notation, okay? So we have a function, and when you have function notation, you have 3 parts, okay? You know that a function matches inputs to output, right? So we have this function. The function is called f. So the function name is f, okay? And that's this
Mm-hmm.
letter on the outside. The number or the expression that's in parentheses is your input. That's your domain values, okay? That's your
Okay.
domain value. That's typically your x, okay? It could be a t or something else, but it's an x number. It's an input value, okay? So this is telling me that this 2 is an input into my function, okay?
Okay.
And then we have an output, which is f of whatever that input is, okay? And that's typically our y value or our range, okay? You
Okay.
with me? So that's typically how this works.
Okay.
Now, if I write this, when is f of x equal to 2? Which one did I give you? The input or the output here?
The output.
Right. So if I go over here now, you can feel free to cheat over here on the right anytime you need to. Okay.
Okay.
If I ask you for f of 2,
Okay.
f of 2, right?
Mm-hmm.
Where am I going to put the 2?
What do you mean, like, put it where? Like,
Am I gonna, okay, how am I gonna find the answer to this?
oh, it's your input,
Right,
right?
so my question to you is, which one of these, if my question is find f of 2, right?
Mm-hmm.
One of these is going to be the correct procedure, one of them isn't. Do I write 2 is equal to 1 over x minus 2? Or do I write 1 over 2 minus 2? Which one do I write?
You're gonna write the second one.
Yeah,
Okay.
yeah, because this is telling me find my output. My input is 2, right?
Right.
So it's this one here. Okay,
Okay.
it's this one here.
Okay, got it.
All right. Now it
Mhm.
happens that in this case, 2 isn't part of the domain of this. And so this is undefined here,
Okay.
right? But
Mhm.
that's the difference between them.
Okay,
Does that help at
got it.
all?
Yeah, it does. Oh my goodness. I was
So
like,
there's a difference between, this is where this comes up. This is
okay.
where this comes up a lot and students get confused. If I give you, here's a function, let's say I give you, let's do x minus 3. I'm not going to make it too hard, but let's do something slightly interesting. I have a function like this, f
Mm-hmm.
of x, right?
Mm-hmm.
Here's my function. Now, pre-calculus will ask you this. Calculus will ask you this for different reasons, but pre-calc is very fond of asking you this. They'll say, find the x and y intercept, but they'll ask it in a different way, okay? They could ask you this way, but they could also say, find f of 0, right? Now,
Mm-hmm.
think about this critically for a minute. I can find f of 0. Am I going to write 0, whoops, 0 equals x minus 3 over x plus 5? Am I going to write that?
No.
Not here for this one, right? Because 0 is supposed to be my what? My input value.
Input. Okay.
Supposed to be my x, isn't it?
Right. Yeah.
So here, this is telling me that x, my input, is equal to 0, and I want to find the output, right?
Mm-hmm.
So here, this is telling me that f of 0 is equal to 0 minus 3 over 0 plus 5, right?
Mm-hmm.
Hold on. My keyboard is 0 plus 5. Okay. So this is equal to negative 3/5. Negative 3/5. Right?
Mm-hmm.
That happens to, now that point is going to be 0 and negative 3/5. So that point is going to be my y-intercept when I do that. If I put 0 in for my input, I'm going to get where it crosses the y-axis. Okay.
Got it. Okay.
Now, if I set this whole thing to 0 here, notice it's not just the input, it's this whole expression now, you see?
Got it. Okay.
Then I'm going to get an x number, and that x number, this might not be immediately apparent, so let me do it this way, right? We're going to cross multiply. Remember that trick? So we're going to say, this. We're going to say 0 times x plus 5 is equal to x minus 3. Now that's going to equal 0. And this is going to be x minus 3, which means that x is equal to 3, right?
Mm-hmm.
Now that corresponds to this point. 3, 0. That is an x-intercept, also called a root of the equation.
Okay.
But that's the difference between the input and the output.
Okay.
All right, does that help?
Yeah. You should feel a little bit confident.
Now let's go back. Let's go back to this for a second here. So, because I think you can put it together now. If I ask you to find f of 2, right?
Mm-hmm.
This is not a limit, is it?
No.
Now, here's the thing. Whatever f of 2 is, okay, it could be the same value as a limit. But if I'm asking
Got
you
it.
to find a limit, limit will be in front of it somewhere.
Okay.
And I know that sounds obvious.
Yeah.
but limit has to be in front of it to find it. Now, if I go back to this, if I talk about f of, say, now let's look at f of 2. Let's say I asked you to find f of 2 here. What is f of 2? What is that asking you to do?
To find the value, right? The f value.
The function value at 2.
Function value. Okay.
Right, so looking at the graph and looking at the equation, whichever one is easier, right? What is
Mhm.
f of 2 here?
It's -1/2.
No, that would
Oh,
be f
sorry,
of
2.
0. That
2.
would, no. F of 2,
F of 2.
look at, where's 2 on this graph?
It's a vertical asymptote.
Yeah, so what does f of 2 equal?
It does not exist.
Right. It's undefined because what happens when I put, remember, 2 goes in my x, right? 2 goes in my x here. So I would get undefined, right? Now, what is f of 0?
F of 0 is 1. So -1, -1, -1.
Are you looking at the graph on my screen? Can you see
Am
it?
I looking at the graph? F of 0? Is that not? Oh, that's -1/2. Oh my, I'm blind. I thought it was negative.
No. Here's, okay, look, love. Here's the function. No, I don't know if you're tired or you really don't get it. I'm gonna harp on it until you do.
I promise I
If
can read a graph. I
f of
promise.
0, f of 0 is -1/2
-1/2. Yep.
right here. Okay.
Yes.
Okay. Let me do
I
another.
promise, Shona, I can read a graph. I
No,
promise.
I believe you, but I want to make sure, that you're actually getting the concept. I'm not sure you do. So let me try this. Let's do this.
Okay.
Let's try this function. Y equals, let's do x squared. No, let's do x to the, let's do x to the 4th minus 3x squared plus 2. Let's do that. Okay.
Okay.
That's a nice, interesting piece of architecture there. Let's do that. And
Okay.
just for fun, let's label some points. -1 and 0 right here. We'll label that one. And we'll label this point down here. So we have, this is going to be negative. I need my function value, so let me pull it up. -√2. Oops. -√2 and 0 right here. And we'll label that point as well. Right there. Okay, let's just label those two. And then let me stop sharing for a second. Now, what is f of 0 here?
Okay. F of 0.
What would f of 0 be?
Can you zoom in a little bit, Shauna? I can't see the numbers on the graph.
Sure, no worries. Look at the function itself.
Okay. So
Look
F
at
of 0, that would be 2.
yeah, this is
Okay.
the 0.02. What did you do to get that?
I inputted 0 into the equation.
Yeah, exactly.
Okay.
So f of 2 is, I'm sorry, f of 0 is 2, right?
Mm-hmm.
F of 0 is 2. So now let me ask you this question. What is the limit? What is the limit as x approaches 0 of this function?
2.
It's 2, isn't it?
Yeah.
In this case, the limit, so in this case, the limit as x approaches 0 of f of x is equal to 2, right?
Mm-hmm.
Now, that 2 is equal to f of 2, right?
Mm-hmm.
F of 0, sorry. F of 0, and f of 0 is 2. So this limit is equal to the value of the function, isn't it?
Mm-hmm.
And what does that mean?
That it's continuous.
That it's continuous at 2, right?
Okay.
Does that help you see it?
Yeah. Yeah.
Now, how does that relate to this? Let me stop sharing this for a minute. And let's look at something over here. I'm going to show you something that I think this is one of those times when, as much as I love Khan is not cutting it. So what I'm going to do here is I'm going to switch videos. Hang on, give me a minute. Now, I'm going to take you through another part of this, another video here, but let me first share the screen so I can show you something about this. So let's see if we can make more sense. And I'm hoping that this guy is not going to let me. He's usually pretty good. Sometimes he's a little much, but sometimes he does a really good job most of the time.
The main idea behind the squeeze theorem is that, let's say that f of x is greater than or equal to h of x, but less than or equal to g of x. So f is between h and g.
Okay, which is
now if the limit
where Sal
as
got
x
us.
approaches
Okay,
some number, let's say a,
he changed his
of h of
letters,
x
but this is
the same
essentially the
as the
same
limit
thing.
as x approaches a of g of x, and let's say that value is L, then the limit as x approaches a of the middle function f of x must also be equal to L.
Okay, so this is basically everything Sal said. Okay, he just changed the letters. Notice F is in the middle, right? F is bigger than H. So H is the bottom function, right? So H is below me. G is above me, right?
Mm-hmm. Yeah.
H, that limit as x approaches A is some number that I know.
Right.
The limit as G approaches A of some number is also L. F is squished between the two, so F must approach L as well. Okay.
If the small function and the large function have a value of L, then the one in the middle should have the same limit L.
Okay.
And that's the main idea behind the squeeze theorem. But let's work on some examples to
Now
apply
he's
it.
going to give you an
So for
example.
example, let's say
Okay.
that f of x is in between 8 minus x cubed and 8 plus x cubed. What is the limit as x
Now,
approaches?
this is a concept. This is not a proof, okay? He's given you this example right now, okay? F of x is between these two functions. So my h is 8 minus x cubed, okay? My g is 8 plus x cubed, right? You follow
Okay.
me?
Shut up. I'm gonna stop my video because it's glitching out. Yeah, it's kind of glitching right now. Again.
Okay. So what
Can
does,
you hear me?
I can hear you. Can you hear me? Can you hear me, Hannah? Hello?
Hello?
I can hear you. Can you hear me? Hello? Hello? Hannah, are you still here?
Yeah,
Okay, can you hear me now?
yeah, that's better. It's like
Alrighty.
glitching.
So this he's building up to a larger proof here. All right.
Okay.
So he's given you a function on this side, 8 minus x cubed. Okay.
Yeah.
And he's given you another function over here, 8 plus x cubed. Okay.
Mm-hmm.
And he's told you that f of x, whatever it is, we don't know. Okay. But
Right.
we're looking for the limit. What he's looking to find is the limit as x goes to 0 of f of x. That's what he wants to know.
Right. Yeah,
Okay.
yeah.
Which is 0 of the function f of x.
Okay.
Well, what is, okay, now he wants to know what this is,
Okay.
right?
Wouldn't, oh, okay. Because you have 8 minus x to the cube. Okay.
So what is, so think about it like this. What is, here's where we're going with this. What is this limit? What is this? What is the limit as x goes to 0 of x of 8 minus x cubed?
Wouldn't it just be 8?
Yeah, don't overthink
Okay.
it. It's not that complicated. Promise you. So that's 8, right? Plug it
Right.
in, you get 8. So that limit is 8, right? What about
Mm-hmm.
the limit over here?
It would be 8.
That would be 8 too. So 8 is, f of x is between two things that both go to 8,
Yes.
right? So what do you think this limit is going to be?
8.
8.
Okay.
That's what the squeeze
Okay.
theorem says, okay? The hardest part of actually using, he's building up, he's helping you to understand this right now. When you actually use the squeeze theorem, these functions that I've circled are not going to be given to you. You
Got
have to
it.
find two functions that your function that you want to find the limit of, you have to find two functions
Oh.
to bind them. Okay?
Oh.
You have to find
Okay.
two functions, or you have to prove it. You have to be given it a graph or something. But the essential idea is once you have these two functions that you can find the limit of, your function is sandwiched between them, and that limit has to be the same. That's what the sandwich theorem says. So we're going to go somewhere. We're going to keep going. with this, okay? But that's the idea behind it. So let me clear the drawings now. And let me continue the video here.
So how can we figure this out? Well, let's apply the limit to every expression in this inequality. If
So he's
f
going
of
to do what
x
we just went
is
over.
greater than 8
Okay.
minus x cubed, and if it's less than or equal to 8 plus x cubed, then we can say that the limit as x approaches 0 of 8 minus x cubed is less than or equal to the limit as x approaches 0 of f of x, which is less than or equal to the limit as x approaches 0 of 8 plus x cubed.
So all he's done
Now
here,
let's go ahead and use direct
all he's done here is said,
substitution.
now I can find the limit by putting the limit in every equation, right?
Mm-hmm.
Every expression. Now, because these are continuous expressions, I can just substitute the numbers directly in, and he's going to do that for you right now.
Okay.
Expression on the left. So as we apply the limit as x approaches 0, this is going to be 8 minus 0 to the third. And the limit as x approaches 0 of f of x is greater than that, but is less than or equal to 8 plus 0 to the third. So this is 8, and on the right side, we also have 8. So therefore, if the limit as x approaches 0 of f of x is greater than or equal to 8, and at the same time less than or equal to 8, we could say that the limit as x approaches 0 of f of x is 8. That's the only way where it could be true.
They're both
It can't
equal
be
to
7,
8. F
because
is
even though
squeezed
7 is
between
less
them.
than 8, 7 is not greater than 8.
Mm-hmm.
And it can't be 9, because even though 9 is greater than 8, 9 is not less than 8. The only way this equation can be true is if we have an 8 in the middle. Then they're all equal to each other.
Okay, he's
Now,
going to
let's
give
work
you
on another
another
example.
example. Now,
Let's try this one. What is the limit as x approaches 2 of the function f of x? And let's say that
okay,
f
so
of
we're
x
looking for that, but here's my function.
is between 5x plus 2 and
Okay.
also is between x squared plus 8. So go ahead and try that problem.
So what do you think, Hannah? Go ahead and try it. Write it out. See what you come up with.
Shauna, it's been glitching out.
Do you see the problem?
Okay. It's I can't even. It's like still glitching out.
So let's find the limit as
Let me stop sharing the screen here. Okay, so this is, okay, hold on. Let me write, hold on. Let me do something here. Let me write the problem out. So if I have, he wrote this, he said, limit as x approaches 2 of f of x if 5x plus 2 is less than f of x, which is less than or equal to x squared plus 8. So here's what he said. I'm going to drop this in the chat here. I'm going to drop this in the chat for you to watch. There you go. Now, we're going to close this. And we're going to close this. So I'm going to bring up
Exit full screen.
the whiteboard. Can you?
You there?
I am here now. Can you hear me?
Oh my goodness, that's so much better.
That better? Did
Yeah,
you
yeah,
get
yeah.
did you get the link in the chat before it died, or do I need to send it again?
It's gonna need to be sent again.
No worries. I would suggest watching that one
Okay.
because but did you figure out what you thought the limit was, or did you not get the problem yet?
I didn't get the problem yet.
Okay, let me put the problem up and then I'll get the video back for you, okay? Let me put the problem on the whiteboard. What he said was, suppose that the question is this. Find the limit as x approaches 2 of f of x, okay, given this, given that I'm going to use parentheses here, 5x plus 2 is less than or equal to f of x, which is less than or equal to x squared plus 8. Okay, this
Okay.
is x squared plus 8. Now, how does that work? Well, remember, we're bounded by these two functions, right?
Right.
5x plus 2 and x squared plus 8. So
Yep.
now we're going to find the limit of each of these parts, aren't we?
Uh-huh.
So we're
Yeah.
going to write the limit as x approaches 2 of 5x plus 2, 5x plus 2 is going to have to be equal, less than or equal to the limit as x approaches 2 of f of x which is equal to, less than or equal to, sorry, less than or equal to the limit as x approaches 2 of x squared plus 8 of x squared plus 8, okay? So what are you going to do
Yeah.
here? What are you going to do there?
Okay. So input 2 into the first equation
Which gives
so
you
that
what?
it's 12.
Yeah, so 12,
And then input 2 into the other equation
right? That's
so that it
also
is
12,
12.
right? So what does
Yes.
that mean for our limit?
That it's 12.
Yeah, exactly. Because
Okay.
it's bounded by two functions whose limits are 12.
Got it. Yeah.
That's,
Okay.
that's what we mean. Now, that's what it's saying, okay? And that's
Uh-huh.
the expression for the that's essentially what the squeeze theorem is saying to do.
Okay.
What we typically use it for, that's kind of the warm up for some of this. Because typically what we do with the squeeze theorem is we prove things, okay? So let me show you Here, let me stop sharing this. And look for, I think I have some. Let me go to my email. But now do you see what it's saying a little bit more?
Yeah, yeah, for sure.
Does that help you see what it's trying to
Yeah,
say?
yeah. So originally I thought it was like, what is this weird thing and why is everything the same?
Well, it needs to be because we need to be able to find the limit, right?
If if one of your equations isn't like, let's say that one is like 5, right? And the other is like 10, does that mean that it doesn't exist?
No,
Like,
it just means they have to be approaching the same number. It means you have to choose
oh, okay.
different. You have to choose different. You have to choose different functions because they have to be
Oh,
approaching the same number in order for that
uh-huh.
to work.
Got it. Okay.
So no, that's a very good question. But that's essentially what that, let me see, squeeze theorem examples. Let me show you this. Let me see if QMath, Grove City College, maybe this one. Let's see if this has any good examples of what we're talking about. Okay, so this one is a good example. Let me drop you this too, just so you can kind of see how an actual proof would actually work, or like
Okay.
an actual more of a. I'm gonna drop this into the chat for you. We're gonna go over it, but I want you to just see a little bit more about how this works, so you can kind of there it is. Whoops. Control V, did I not? There it is. All right, there's the PDF handout for that.
All right, thank you.
And what I'm gonna do now is I'm gonna bring this up into the share screen. Now we typically do this, we don't have to do this with trig functions, but we typically do this with trig functions. So this handout starts where both of our last videos started, with an explanation of the squeeze theorem right there, right? G is
Okay.
between
Yeah,
F
yeah.
and H, and the limits are going to L, so G is going to L as well. Now, suppose we have this limit as x goes to 0, x squared cosine 1 over x squared, okay? Now, remember I told you that we're not given the functions, right? Typically, we're not given the functions. We have to find them, right? We have to know what they are. So here's the little explanation. When trying to find functions to use to squeeze g of x, we want to find functions that are similar enough to g of x that we can be sure the squeeze theorem works. So we want to know that they're basically similar enough that I'm actually going to be able to squeeze g between them, right?
Right. Right.
And we want to be able to evaluate the limit fairly easily, certainly easier than this thing that we can't evaluate right now.
Right. Right.
Because we're doing the squeeze theorem because we can't evaluate the limit. We don't have a way of doing it. So we need to find functions that are easier than the one we have, but are related enough to be able to evaluate the limit of, okay?
Mm-hmm.
So how do we do that? Well, we typically do this by starting with the most complicated or troublesome part of g of x. So what is the part of this function that we're given that's the most nasty? We could deal with this x squared, right? That's a
Right.
nice polynomial. That wouldn't be a problem. It's this it's this thing here. Even the cosine is not too bad, right? Cosine,
Yeah.
we deal with cosine. It's this ugly argument in the middle that we're nasty,
Right.
right?
Yeah.
So we
That's it.
typically do this by starting with the most complicated part and see if we can find constants or simpler functions that it stays between, okay? And then multiply the rest of the nicer part of g of x. Now, that's a lovely explanation, but what the heck is it saying?
Yeah.
What it's saying is this. Start, this is ugly. We agree, this
Uh-huh.
is ugly. But if we start with this, we know something about cosine x.
Right.
This is where we draw on our trig knowledge, right? What do we know about cosine x? We know that cosine x is between -1 and 1, don't we?
Yes.
So what I'm going to do here is I'm going to undo this ugliness over here. So this is -1 less than equal to cosine x. And this is less than equal to 1, right? And you're thinking, well, that's great. We've got a cosine, but what about this ugly argument? We'll get to that, okay? So what they're going to do is, in this case, the part of g of x that's giving us the problem is this cosine 1 over x squared part, right? So we know that cosine x stays between -1 and 1, right? So whatever this argument is here, right? This argument, whatever it is, this argument here is going to be between -1 and 1, isn't it?
Uh-huh.
So
Yeah,
I
okay.
can say that -1 is less than equal to cosine 1 over x squared is going to 1, right? Because this is just an argument of cosine, right?
Yes.
Now, look carefully. Let me take away this mark here. Now we're almost there. Look at your limit up here and look at the result that you wrote down below just based on what you knew about the cosine, right? See that? So this piece
Yeah.
here looks almost like this piece. What's missing from it? You've got the 1 over x squared. See?
Right.
You've got
Oh,
the
the x squared in front of
cosine.
it, right?
Yeah, you don't have this x squared in front of it, right?
Okay.
Now, x squared is always positive, isn't it?
Yes.
Because I'm
Yeah.
squaring a number, right? So if
Uh-huh.
I were to do something crazy, like multiply this whole inequality by x squared, right? X squared times -1 would give us -x squared, wouldn't it?
Uh-huh.
And then x squared times this would give us, look at this, would give us the function we have in the middle, doesn't it? See that?
Right.
And
Yeah.
that's equal to x squared there. Now, why is this important? Okay. First of all, because I multiplied by x squared, right? I don't have to worry about this inequality changing direction or doing anything weird, do I? Because I multiplied by a positive number. But more importantly, can I find the limit as x goes to 0 now?
Yeah.
Yeah, because can I find the limit of this?
Yes.
Yeah. Can I find the limit of that thing on the right?
Yeah.
Yeah. And if I can find both of those limits, then I can find this limit in the middle that I didn't know.
Got it. Okay.
So
So
this,
then, wait, Shauna, I have a question.
yes.
So if the left side turns out to be like 1 and the right side turns out to be 1, does that mean that in the middle it's 1?
Yes,
Okay. So then you don't have to solve that.
because it's less than or equal to that number, right? So
Okay.
if they're both equal to each other, it has to be that number, right?
So then do you have to find that crazy, do you have to do anything like algebraically in the middle, or is it just,
Well, think about what you just said and see if you can answer your own question. If both sides of it were 1, right?
uh-huh,
Then what is the middle part?
1?
It has to be. Why?
Okay. Oh,
Because
okay.
think about, before we come back to that, think about this. Remember this example here? Well, you probably would if we could. There's my whiteboard, right? There it
Okay.
is. When I did this limit here, right?
Uh-huh.
This side, this left side was what?
12.
12. And then that's equal, less than or equal to the limit as x approaches 2 of f of x, which is less than or equal to 12 over here, right? And if you remember watching the other video that we did,
Mm-hmm.
if this is 12 as well, then do we have to do anything fancy in the middle?
Mm.
What do you think?
No,
Why not?
right?
You're correct. Why
Because
not?
according to the squeeze theorem, that
Uh-huh.
if the left side is 12 and the right side is 12, then that all three of the functions have to meet at 12.
Yes. That's exactly what the squeeze term is saying.
Heck yeah. Okay, here we go.
Right?
Yeah. Okay.
The difference between the two examples that I've shown you in trying to get you to understand what it actually means
Yeah.
is that typically when we do the squeeze theorem here, typically when we do it from scratch, we're not given these functions.
Right.
Okay. We have to find those functions. We have to choose those
Right.
functions.
Okay.
Okay. We have to choose them. And so typically what happens, that's why over here, you typically do squeeze theorems on a lot of trig functions. That's typically where you see it the most. You don't have to, but that's typically where they show up the most. Is that we start with something here. Let me scroll up just a bit. There we are. We start with, hold on, my cursor really wants to show you example 2, but I don't want to show you that right yet.
Might give me a heart attack.
No, it's not that bad. There's my example, right? So again, we knew what cosine was doing. We had an x squared there. So we just multiplied by the x squared, didn't we? And we could find the limit. This was 0. The other side was 0. So that limit had to be 0, right?
Right.
Now here's another one. Look at example 2 right here. Look at example 2 down here. See it?
Yeah.
Now here we have x squared times e to the power of sine 1 over x.
Okay, I've been getting a couple like problems on my homework with E, and I have I don't get them. Like maybe it's because like I don't know. There's something about
You
it that I'm like,
mean limits or evaluating functions?
no, I mean like just E, like the X, like as a natural log and all those things. I'm like,
Okay,
I'm like,
okay.
"Eh,
Well,
scary.
this proof, I'll leave this for you, okay?
Okay,
But this is based on sine, okay?
okay,
So sine of x, or sine of 1 over x, or sine of anything you want,
right.
this portion here has to be between -1 and 1, okay?
Okay.
So then what you do is you raise e to both sides,
Mm-hmm.
and then you can continue from there. But that handout will give you some insight into how using
Okay.
the theorem will actually help you to find limits, okay?
Okay.
Now, coming back to what I think your question is, it depends, because you could be doing derivatives, you could be doing a lot of stuff, I don't know. But let me start by saying this. Let me start by saying that E is a number like pi, okay? So you're very familiar with pi, aren't you? This thing here. Does that look familiar to you? Hannah?
Can you hear me?
Okay, you're back. So
Okay.
I
Sorry.
I was saying to you that to start this, E is a number like pi, okay?
Okay.
Think of pi, right?
Mm-hmm.
What do you know about pi?
It's infinite. Goes on, or well, it goes on
Well,
forever.
it repeats infinitely, so it's irrational, right?
It's irrational.
What else do you know about it?
It's 3.14,
Yeah,
and then
etc.
a bunch of numbers.
But it's a constant, right?
Right.
It's a constant. E is a constant as well, okay?
Okay.
So E is one of those constants like pi. The
Okay.
constant E is called, it's the base of what we call the natural logarithm, okay? We have two major forms. Well, we have more, but we have what we call common logs and natural logs. Okay, does that sound
Uh-huh.
familiar
Yes.
to you? So,
Yep.
okay, so E is a constant, like pi is a constant.
Okay.
E is approximately 2.718, okay? I don't have any
Okay.
more of the decimal places memorized, but it is irrational as well, okay? And
Mm-hmm.
E shows up in a lot of natural applications in biology, chemistry, and other sciences, okay? So that's
Uh-huh.
just a little background on that. So it's just a
Okay.
constant. It's just a
Got
constant like pi, right?
Okay.
So I can do stuff, we can do stuff with like, are you confused? Are you doing anything about like ln of e squared?
We did a couple, and I probably should know how to do that, but
Okay.
it
So
gets confusing.
that goes back to the discussion on logarithms, okay?
Yeah.
Which is algebra, okay? but but we can yeah, so
I mean, it's not, I mean, I don't think it'll be too big of a deal on my test. It's just, you know.
but just to let you know, just to kind of fill in some gaps, okay?
Okay.
We have, you've seen the log of, let's say, 100, right?
Great.
Or you've seen things like ln of e squared, for example, right?
Uh-huh.
Now, log of 100, notice I don't have a base written down here.
Okay.
You see?
Mm-hmm.
I just have log of 100, okay? So if I don't have a base written down here, we understand that to be a 10. Okay?
Okay.
We don't write the 10. I'm going to write the 10 for you here. We understand that to be a 10. Okay? This is what we call the common logarithm
Okay.
or the common log. Now, e, as I said, is a constant, right?
Mhm.
And because it shows up so often, and because it's so used, it gets its own logarithmic symbol. So
Okay.
instead of writing, now we could write this, we could say log base e of e squared. I could write that, right?
Right.
That's legit. Only I never do. This is
Okay.
not something we write. Because if e is a base of our logarithm, then it has a symbol of its own, and we call that ln.
Okay.
ln of e squared. Okay? This is called the natural logarithm. Okay? So the common logarithms have a base of 10. And the natural logarithms have a base of e. Okay?
Oh,
Hi, are you there?
hello.
Hi, Hannah,
Yeah.
can you
Okay.
hear me?
Yeah. Perfect.
They have a base of e, right?
Okay.
So that's where we're going with that part of it. And you can do things like you can move the properties around. You can find limits, right? So let me
Uh-huh.
just show you something here by way of kind of addressing, not necessarily answering everything, but maybe help you see where this is going. If I go and I say, let me take you back to our lovely friend Desmos again here.
Mm.
I want to just show you something. So this goes back to algebra again, but again, I'm going to do the share here for you. Here's my function. Let's just graph y equals e, and there's my number. See it? 2.71828182846,
Uh-huh.
right? e
Yeah,
to
yeah.
x power.
Okay.
The graph looks like this. So it's an increasing function with a horizontal asymptote at the x-axis, and it goes through the point 0, 1, right? Because e to the 0 is 1. So if I asked you for the limit, if I said, what is the limit as x approaches negative infinity? Let's say I wanted to
Okay.
do that. The limit as x
Uh-huh.
approaches negative infinity. Remember, negative infinity is over here, right?
Okay.
This is negative infinity, right? So what I'm looking
Right.
at is I'm looking at this. My function, I'm approaching negative infinity. I'm getting smaller and smaller and smaller. What is my y approaching?
Your y is approaching. Wait, your y, isn't it the x? Right?
X is
Wait.
getting smaller and smaller.
Okay, x is getting smaller.
So here's my x getting smaller. This is 0, right?
Right?
This is negative
And
1 over here,
right?
right? This is negative 2 over here. What
Yes.
is y getting close to?
Oh, 0.
0, because it's getting really close. It's asymptotic to the x-axis, right? So the
Yeah.
limit as x approaches negative infinity of e to the x is actually finite. It exists and it's 0. This is e to the x power, right?
Right.
Is equal to 0. Okay?
Yeah.
Now you can do a lot more with that because there's more properties. What would you say the limit is as x goes to positive infinity?
As x goes to positive infinity, that would be, is that 2 that it's
Well, be careful. I'm
approaching?
going to positive infinity, so I'm not going to 0 here, right?
Okay. Oh,
I'm
you're okay, you're going,
positive infinity. So what's happening to my y value?
it's reaching positive infinity.
Yeah. So in this
Okay.
case, the limit as x approaches positive infinity would be infinity, right? It's
Right.
growing without bound, or it doesn't exist. It's growing without bound. But the limit as x approaches negative infinity is 0.
Okay.
Does that help?
Yeah.
Does that help you see it more?
Yeah, it does.
I don't know what else you need to cover, hon.
I know. I'm like, I don't know, I think I'm freaking out for no reason.
Well, what's making you
That last quiz. That last
okay.
quiz.
Okay.
Just like, I don't know. I like kind of
Are
threw
you
me off
are
my
you
game.
learning about the Rolle's theorem and some
Not
of
yet.
the Rolle's theorem and the mean value theorem too?
Not yet. No.
Okay. Because they're coming, but they usually come up in the context of derivatives when you start looking at the slope of the secant line.
Okay.
So they're coming, but I don't know how far down the pike she is because this lady is teaching. But when you said she was teaching random stuff, like what is the
It just,
random stuff that you're referring to?
well, I kind of got, I kind of got mad because we were doing it in class with like in groups and stuff, and I sit in the front now,
Okay,
because I can't see in the back, and she had me in
right,
the back, and I couldn't.
right.
So I made a stink because there was something that we hadn't learned yet, or at least something I didn't think we had learned. And so I
Uh-huh,
made a stink about it, and I was like, and I kind of got a little loud, and I was like, "What?" Because it was a linear function. Okay,
okay,
it was a linear function, and it said that your f of x represented, what was it? It represented distance, and the other one represented distance, and the other represented like something else. But
okay,
they wanted, oh, I think it was time, and
okay,
they wanted you to find speed.
okay.
And I was like, what? I was like, we didn't do this. And then my teacher goes, honey, it's just common sense. And I was like, oh, okay.
Distance equals rate times time, Hannah.
That's what I was saying. I was like, so we're going to use the dirt formula, right? Distance equals rate times time. Because for some reason, that is the only other formula besides y equals mx plus b that I have fully memorized. And I was like, the dirt formula, right? And she goes, no. And I was like, okay, then what do you do? She goes, you look at the graph and you just know. And I was like, what? It's like, okay. Because I
Well,
guess because,
the thing is, you're learning to interpret it a different way. Where she's going with this is a graphical interpretation of what those applications are.
okay.
Because believe it or not, it has applications, a lot of applications in calculus and physics. So
Yeah.
she's
Well,
probably
luckily,
getting you, she's probably getting you to see that right now, even
yeah.
though you could have used that. But that's probably, that would be my guess without seeing the work.
Yeah. Luckily, a kid next to me took physics because I never took physics because I took AP biology instead of
Right.
physics. And he was like, oh, he goes, oh, it's just physics. And I was like, that's great, but we're not in a physics class.
No, but what they do is uh they teach you some applications that show up in different versions. So what I'm gonna do right
Oh,
now, they show up, and that's a very common, but that application isn't just physics, but it tends to be like it's a fundamental example of it because it's very similar. So it shows up, it's one of those examples that shows up in a lot of classes,
okay.
and that's why. So if he was probably excited because he recognized something.
Yeah.
He's like,
He was like, he's like, this is just physics. And I was like, that's great. I didn't take physics. Like,
no, but
and then she was like, but yeah, the way that she said that, she was just like, honey, it's so simple. And I was like, okay. And she was right. I mean, it was pretty easy because it was like, it went straight, it was like a straight, it went up, right? It
uh,
increased,
it
and
increased,
then
right?
it leveled out, then
Uh-huh.
it leveled out, and then where the point was that it had given you, it did
Right.
level out, so it meant 0.
Uh-huh.
I got that later on,
Yeah,
but
no,
I can get where she's going with.
it takes a while sometimes. I'm sending you a bunch of stuff, so don't leave me, but I think we should pray for this quiz. How was
Oh,
how is your teacher's grandson doing?
she seems to be, I think he's doing better because she seems to be happier. So I was like, how was your weekend? And she goes, it was really, really good. And I was like, oh, that's good. That's great. And
And
then
you were like,
her and I
thank
were
God.
talking about this. Yeah, I was so excited. I was like, that is so awesome. And she made a comment. She was like, it was weird. It was kind of, I was like, oh, okay. She goes, how many of you in here are praying for my grandson? And we got a lot of
Oh,
atheists in my
really?
class, a lot of Buddhists. There's probably a lot of Buddhists in my class. Now I'm generalized, but there's probably a lot
Really?
of Buddhists in my class, and like no one raised their hand. I raised my hand. I was like, I am. And she goes, Hannah, I know you're praying. And then another girl raised her, and I was like, oh, that is
Aw.
so cool. Like that's pretty cool. Like that's cool.
Well, no,
But
Buddhists pray too, but I don't know that, you know what I mean?
yeah, I don't know
There's
their
different.
logistics either.
Okay, your whiteboard, your screenshots. Let me make sure you have your video link. Let me find the video that I was giving you to watch because that's important. Let me go to the history here. And we'll pick it up. And I can I'll give you this link. So let me just click this. Okay. And I'll resend you here's the the organic chemistry tutor, speech theorem, organic. This guy tutors a lot more than just chemistry. He's really good,
Okay.
actually. He has a lot of videos. And they tend to be, sometimes they're a little bit much, but he tends to do a really good job. Khan, as much as I
Thank you,
love
Shauna.
Khan, sometimes Khan is a bit, it lacks a bit. And then here was the squeeze theorem examples, which I also I just want to make sure you have everything that we discussed, because here it is. This is the squeeze theorem handout right here. So this is going to be here. And this should be plenty of material for you.
All right, thank you, Shauna. I appreciate it.
And I will, after we finish our Zoom and the meeting has rendered, I'll send you the video link, but I didn't want you to not have that to study
You want to
on.
say hi to Shauna, Mom?
Hey, Gloria.
Hey, Shauna.
Trying to take care
What's
of your
going on,
daughter
Shauna?
here. We're trying
Oh
to
my God,
we're
what's
trying to
your
do
daughter?
some calculus.